am Shantanu Ghosh, and for the course Introduction to Solid State Physics, I will solve assignment 1. So, assignment 1 I will solve. For the first question, it is given that question number 1, take a straight metal wire, that is 1D, and we want to find the specific heat due to conduction of electron, which will satisfy Drude's theory. Now, we know that Drude considered electrons as kinetic theory of gases. He applied that kinetic theory of gases, the free electrons, and we know that from the equipartition theorem that energy for every 1 degrees of freedom is half kT. Now, suppose we can assume that there are n number of electrons, n is the Avogadro number. So, total energy is half kB n T. This half kBT comes because we have one dimension. So, the electrons can move in only in one direction. So, we have 1 degree of freedom. So, here we get half RT. So, specific heat will get del U del T and it will be half R. So, correct option is option T. Moving to the next question, question number 2. We got that a metal has very large scattering time, and we take it tau equals to infinity. Now, using Drude's model, in the presence of a DC electric field, what will be the current density? So, according to the Drude's model, we have dP dt equals to Ft minus Pt by tau. This is tau is due to scattering, and this dP dt is rate of change of momentum, and Ft is the external force. So, here suppose we have a DC electric field V, so force will be Q into V. Suppose it has charge Q, we have of the particle charge Q. Now, tau equals to infinity. So, this term due to tau equals to infinity will go to 0, because 1 by tau, 1 by infinity, we can take it to 0. So, we take dP dt equals to Ft. Now, Ft is we have Q into V. So, we can write dP dt as m into dV dt equals to QV, because we know that P equals to mV, and we know that J equals to NQV. This V is the velocity, this del V del T, this is the velocity V, and this is the potential V. This is small v, this is capital. This current density J equals to NQV. So, we can replace V by J by NQ, and we put this here. So, we get m into 1 by NQ dJ dt equals to QV. So, we see that everything here it is constant, dJ dt is QV NQ by m. This is constant we can take, because we are applying a constant electric field, and everything m, n and q both everything is constant. So, from here we take J equals to kT. By integrating we can get J equals to kT. So, it is just linear graph J versus T passing through origin for tau equals to infinity. So, it is option A. Moving to the next problem, question number 3, sketch the behavior of specific heat of a pure 3D metal as a function of temperature. So, this is Cv versus T. At higher temperature, we know Cv is 3R, this is according to Dulong-Petit's law. Dulong-Petit's law, it is Cv equals to 3R at high temperature, and then due to lattice vibration it is moves as Tq, Cv proportional to Tq, and at this is due to the lattice part, and at very low temperature when the lattice vibration is switched off, then we have the electronic contribution to the specific heat, electronic contribution here, contribution. So, here Cv is proportional to T. So, we have this graph. At high temperature it is constant, along this mid temperature Cv falls down as Cv proportional to T cube, at a low temperature it is linear. So, the correct option is option B. Moving to the next problem 4. So, electrons are drifting in a metal with average velocity V naught and electric field E is present. At T equals to 0, E is 0, electric field is switched off. Okay. Then what will be the time dependence of the average velocity with respect to time? So, again from Doods model we know dp dt equals to ft minus pt by tau. Now, for t equals to 0, here electric field is 0. So, ft q into E we can take it to 0. So, dp dt equals to minus pt by tau, and solving this we get pt will be p naught e to the power minus t by tau. So, our correct option is option A. For the next problem, problem number 5, which can have both negative and positive Hall coefficient RH. We know the form of RH is minus 1 by n. Now, for a doped semiconductor, suppose it is an intrinsic semiconductor and the carrier charge is electron. If we dope some holes in the semiconductor, so electrons are always present, and now we dope some hole. So, now both electron and hole are present. So, they both can carry charge and they both can contribute to the current. So, this RH is, this negative sign is for the electrons and RH will be positive for holes, as both are present. So, RH can be both positive and negative. So, the correct option is B. Moving to the next problem, question number 6. We have tau equals to 10 to the power minus 15 second. What will be the momentum pt after some time interval dt equals to 3 into 10 to the power minus 16 second. So, again here we get E equals to 0 and B equals to 0, it is given. So, external force is 0, external force on the charge will be 0. So, Ft will be 0. So, we get here that from again the Doods equation dp dt equals to Ft minus Pt by tau, Ft is 0 we have. So, dp dt minus Pt by tau. This dp dt we can write this as Pt plus dt minus Pt, and dt we have 3 into 10 to the power minus 16, and this Pt is minus Pt, tau is given as 10 to the power minus 15, 10 to the power minus 15. So, we have Pt plus dt minus of Pt, we have minus Pt into the 3 into 10 to the power minus 16 by 10 to the power minus 15. So, we get here this will be 10 to the power minus 1. So, we have minus 0.3 Pt. So, after a time interval dt, so Pt plus dt, the value of momentum P after some time interval dt will be Pt minus 0.3 Pt, 0.7 Pt. This is option A. Now, moving to the next problem, question number 7. A metal is subjected to an electric field. We have electric field is given as E naught e to the power minus I omega t, and relaxation time is given as tau. So, what will be the form of v? So, here we assume that, and it is given also, that velocity has same time dependence as the applied electric field. So, as this is electric field as this time dependence, we can write V t equals to V naught e to the power I omega t. They have the same time dependence. So, now we just note this down, and now again we will solve the Drude's equation. We have dp dt equals to f of t minus pt by tau, and here f t we will have minus e into naught e to the power minus I omega t. This minus comes due to electron has negative charge. So, now the Drude's equation will be dp dt equals to minus e naught e to the power minus I omega t minus pt by tau. We put p equals to mv. So, we get m dv dt will be minus e naught e to the power minus I omega t m v t by tau. We divide both side by m. So, we get dv dt will be minus e naught by m e to the power minus I omega t minus v t by tau. Now, we put the form of v t that we considered v t equals to v naught e to the power minus I omega t, as the v t and f t both have the same time dependence. So, we put this value of v t in this equation and we get, it will be differentiated. So, we get here minus I omega v naught e to the power minus I omega t. By differentiating this dv dt we will get this easily. Dv dt will get this value easily. So, minus e naught by m e to the power minus I omega t minus v t again v naught e to the power minus I omega t by tau. We got all the e omega t part. So, we have v naught by tau minus I omega v naught. I just took this term in this here. So, minus e naught by m. So, from here we can take v naught will be 1 by tau minus I omega minus e naught by m. So, v naught will be minus e naught m 1 by tau minus I omega. So, our v t will be v naught e to the power minus I omega t, and we just put this value I omega t. This will be m minus I omega plus 1 by tau. This is option C. So, next question, question number 8. Using the equation derived above, find the frequency dependent electrical conductivity. So, we know that J equals to minus NeV. We can take in this minus sign due to electrons, and so J will be n square E naught e to the power minus I omega t by m minus I omega 1 by tau, and this comes just from the previous expression. For the previous problem we got V equals to minus E naught e to the power minus I omega t by m minus I omega 1 by tau. So, we got this here, and we know now that J, the current density, is electrical conductivity into the electric field. So, we put the values here and here. The J will be n square E naught e to the power minus I omega t by m minus I omega 1 by tau, sigma electric fields is my e to the power minus I omega t. So, just for the same previous problem we have that. So, we cut them. So, sigma omega, we take this as function of omega I cannot, because here is omega is present. So, here we get sigma naught by 1 minus I omega tau, where sigma naught is n square tau by m. We can just make this tau, this will be tau minus I omega tau plus 1 simply, and this tau will go on the numerator, and thus this is the DC conductivity of the metal. So, we get that frequency dependent electrical conductivity will be like this, and this is option A. Moving to the next problem, we want to find the expression for the mobility of the electrons. The mobility of the electrons are defined as, this is mobility, mobility of the electrons, we define this as velocity, v is the velocity of the electrons minus mu e into electric field. So, again now from Drude's theory we got dp dt is ft minus pt by tau, and here we put the value of v here because p is we know mv, and by putting we get that me mu e d dt, because dv dt will be minus mu e d dt. So, because mobility is constant with respect to time. So, minus e t, just the force will be this, and plus me by tau mu e et. We just replacing the value of v by this value. So, we consider steady state, we can consider that after a very long interval of time, that with respect to time the system does not change so much. So, steady state we can write d dt 0 after a very long interval of time. So, if this part is going to be 0, so here from here we will get mu e by equating this to taking this term here, this is already 0. So, this equals to this, and from there we get mu e equals to e tau by m. This is option A. Next problem, question number 10. Mean free path of an electron Le, this is mean free path, this of a 1D wire made of copper, at we have copper wire, and this is the mean free path, at 300 Kelvin is, what is the order? We have given tau equals to 4 into 10 to the power minus 14 second. So, now the mean free path will be the mean thermal velocity into the relaxation time, the time required for the two successive collisions. Suppose there the electron has one collision and here another, it again collides, this time suppose to travel this, it takes time tau. So, this is the relaxation time and the length is L, mean free path, and V is the thermal velocity, mean thermal velocity, and here it is one dimension. So, we know that mean thermal velocity will be root under kT by m. Just we can get this V thermal square equals to half kBT, from there we can easily get, and this is our V thermal, tau is my given here. So, L will be root under kT by me into tau is my 4 into 10 to the power minus 14. We know this me value of mass of electron, k value we know, T is given at 300 Kelvin. So, just by putting and C we will get 24 angstrom, approximately 24 angstrom, option A. Now, moving to the next question 11. Density of copper is given as N equals to 8.45 10 to the power 28 meter cube. So, Hall coefficient, what will be the Hall coefficient? So, Hall coefficient is given by this, N is given here, we know the charge of electron. So, by putting the all values, we will put the values of N, and charge of one electron 1.6 10 to the power minus 19 coulomb, and putting this we will get the value minus 0.73 into 10 to the power minus 9 meter cube by coulomb. This is option A. Just put the value and calculate, it is just trivia. Moving to the next question, question number 12. We have that RHS and RHM. This is for a semiconductor. This is semiconductor, the value of Hall coefficient, and this is for metal, the value of Hall coefficient. Now, what will be the proper relation? This is the question. Now, we know that RH is simple as that, 1 by NE, value of Hall coefficient. So, I can write RHS, this is for the semiconductor, 1 by NS, 1 by E, and RHM will be minus 1 by N for M, 1 by E. So, this is for the semiconductor and this is for the metal. So, now we already know that for a metal the number of electrons will be always higher than a semiconductor. So, number of free electrons rather. So, this will be this. So, we get this 1 by, so it will flip sign. We can put the value of minus 1 and we will just can multiply both sides by 1 by E. So, we get RHM will be less than RHS. This is option A. Moving to the next question, question number 13. Here, according to the Drude's model, the longitudinal resistance of metal when B is applied is, okay, this is for the Hall effect problem that is done by Professor Satyajit Banerjee in his lectures. So, if I can see that in this sheet the current is moving through here and I want to measure the voltage along this edge or the thickness, and here the magnetic field is applied along this direction, along the width, actually I was mistaken, the voltage was measured along the width, and so we will see that the electric field will be 1 by NE J B naught x cap. We take the coordinate axis as x cap, y cap, z cap. So, x plus m by n is square tau j by y cap. So, we see that the longitudinal part is along this direction, this is my longitudinal direction and this is transverse, this direction is transverse, can you say. So, you see that the transverse direction is along x direction, x cap, and longitudinal is along y cap. So, along the y cap here we see that there is no B naught term. So, it does not depend on the magnetic field. So, if we switch on or switch it off, it is just the E equals to rho j part. So, there will be no change for the resistivity along the longitudinal direction, the only change will be along the transverse. So, here del rho equals to 0, but actually this is not rather correct. There is some longitudinal resistance change along the longitudinal direction and that is called magnetoresistance, but according to Drude's theory we can't explain that. So, it is actually one of the failure of Drude's theory. So, this is option A. So, the last question, question number 14, it is given as, this is my sheet is given, this is B 1.0 Tesla, this is T, this is width, this is my T thickness and this is my length. So, there is current moving there and we want to calculate what will be the Hall voltage along this direction. Okay. So, we know that along this part from the lecture you can also see EH will be rho h into J. This is the Hall resistivity, and J is the current density. So, EH I can write is at VH by W, because now VH is measuring along this direction. So, the distance between the two probes of the voltmeter is W here, it is not this along this length. So, VH by W rho h, J will be I by A. This is current density, means current per unit area. So, area is omega into T, W into T. So, I by A, so this will be I rho h into I by W T. So, W will get cancelled out. So, V h will be rho h by T into I. Now, rho h, we know that rho h is given as R h by B naught. R h, this is copper sheet, it is given, and this R h for copper is, we have calculated this already for question number 11. From question number 11 we know the R h of C copper is almost 0.073 into 10 to the power minus 9 meter cube per coulomb. So, this is, so we get that V h will be R h B naught by T into I. This, putting all the values, we know the R h from the previous one, B naught is given 1 Tesla, current is given 1 milliampere, it is 1 Tesla, and T is my 1 nanometer. So, by putting the values we will get almost minus 4 volt. So, this is your option D. So, actually the assignment that has been the solution is uploaded version, it was wrongly written as option